Okay. How many? 59. Okay. Okay. I have 3 announcements today. The first one, the book I wrote. This book is available in online and offline bookstores. I checked Unistore and our campus bookstore, and they have that. They have the books in stock, so you can go to the Unistore as well. Second announcement is about lecture video posting. You know, I'm recording this video and trying to upload the lecture after the class. But the problem is I'm allowed to use only 3 GB. I'm allowed to use only 3 GB of storage. 3 GB of storage on Blackboard. So I cannot post all the lectures on Blackboard. So probably I have to keep only 3 lectures, because each lecture takes roughly 700 to 800 megabyte each lecture. So I'm able to keep only 3 lectures posted. Okay, so that means I have to delete all the lectures to upload the latest. Okay, so please keep that in mind. If you need the lecture, probably you can download it, okay, beforehand. And the last announcement is about the first assignment. Actually, I posted this first assignment last week, and it is about it is very related to today's lecture. Okay, today's lecture, the Lec2 cross compiler installation. Okay, we are going to use that cross compiler throughout this semester. So the due is next Wednesday. Okay, midnight. Okay, midnight of next Wednesday. Okay, that is the one. So after today's lecture, you will figure out what you have to do. Okay, regarding this first assignment. Okay, let's get started. Okay, today we will talk about the instructions. Okay, CPU is providing instructions, machine code, instruction or machine code, and how high-level code, for example, written in C language, high-level code is translated to machine code, CPU understandable code. Okay, translation from high level to machine code, high level to or instruction, high level to machine code. Okay, this one, Yusang, can you please?
Yes. Abstraction helps us deal with complexity, high, lower level detail. Instruction set architecture, ISA, an abstraction interface between the hardware and the low-level software.
Okay, abstraction, thanks. Abstraction is so important concept. I want to repeat the concept, abstraction. Abstraction is helping us deal with complexity. It is hiding all the low-level detail, right? So I showed you these 2, analogies, right? So the combustion engine inside the car and brake system inside the car, right? So to drive a car, you don't have to actually understand the machine detail of this engine system and brake system, because this dashboard, that is hiding all the low-level detail, right? So you don't have to worry about, okay, don't worry, this dashboard says, don't worry about this, too complicated. What you have to do is to drive forward. You have to shift this gear to the drive position and step on accelerator, then car will move forward, right? Abstraction layer, it is hiding this dashboard, hiding all the low-level detail. Same thing goes to this box, the vending machine box, right? Inside this vending machine, there is a little bit not that complicated, but this hardware system. But customers, okay, general people, right? People don't understand how this hardware system works. Nevertheless, they are able to take out Coke, Sprite. How come? because this box is providing abstraction layer. Don't worry about this the hardware detail. Okay, all you have to do is insert coins and press the button. That's it, right? Hiding all the low level detail. Same concept applies to all electronic devices and mechanical devices, right? The computer, right? So that is computer hierarchy. If you open this box, this desktop computer, the most important component in this computer is called CPU or processor. Okay, that is the brain, right? But I told you there are 100,000 employees, 100,000 employees worldwide at Intel, right? There are several departments, right? Marketing, research, design, human resources, many departments. But essentially, all those people are there to research this chip, design this chip, manufacture this chip, promote this chip, right? Sell this chip, right? So it's super complicated hardware component, okay? And even inside the Intel, only few people, really, only few people understand all the nitty-gritty detail of the chip. Very complicated. That is why Intel is providing this abstraction layer, which is called instruction set. Instruction set or machine code. We said machine code. Look at this, ones and zeros, machine code. This machine, this CPU only understand, this, machine code, ones and zeros. We call that machine code or instructions. In Korean, 명령어, right? 명령어, instructions. Okay, that is instructions or machine code. What is machine code in Korean? 기계어, right? Okay, instruction or machine code. And if you look at this machine code for 1 minute, then it's still complicated, right? Ones and zeros, right? You don't want to look at ones and zeros, right? You look at this machine code for 1 minute, then your eyes are spinning, right? Brain stops, right? You don't want to look at this, right? That is why computer is providing another, abstraction layer, which is operating system. Okay, so Windows, Linux. In case of smartphone, right? iOS or Android, they are providing abstraction layer. What this guy says, okay, don't worry too much about this instruction machine code. Okay, hardware design, hardware detail, forget about this, too complicated. What you have to do is on Windows, when computer boots up, what you have to do is click on that icon, click on this icon, okay, CPU G, for example, to figure out your machine configuration. Okay, to cook up documentation, click on MS Word icon. Then nice window will pops up. You can hook up your documentation. So that is providing abstraction layer. This one is abstraction layer. It is essentially managing or hardware or CPU, memory, hard disk, I/O devices. It is managing all different hardware. Okay, for you. And on top of this, you are developing your application programs, right? For example, last year you took C language course, Java language course, right? And Python, right? So you were here on top. Okay. Then someone, if you write C code, if you write Java code, someone is translating that code into CPU understandable code. From here to here. From high level code to this machine code. Who is doing that? Compiler, right? Compiler, C compiler or Visual Studio, right? GCC, if you use your Linux. If you write code On Linux, you use GCC. And if you develop software on Windows, you use Visual Studio, probably Visual Studio compiler from Microsoft, GCC or Visual Studio compiler. Right? So compiler is translating high-level code into the machine code. Because the code is now code is now can be taken by CPU. CPU now understand the code you wrote because that got translated by compiler. So CPU takes those machine code and execute it. Okay, so that is a big picture. So again, I want to emphasize this concept. Abstraction. You need to see the big picture first, right? If you cannot see the forest for trees, that is not going to be effective, right? In this whole picture, in this computer science forest, in this course, we are here at the bottom layer. Okay, computer architecture course, we are talking about the very bottom layer of the abstraction. Okay, so in this class, we are going to study machine code or instruction. RISC-V CPU is providing. Again, right? We are going to talk about this CPU, RISC-V. This CPU is providing, and I'm going to show you how to design digital logic, how to design this CPU logic to execute the machine code. RISC-V is providing. Okay, so CPU, our CPU, our RISC-V CPU, your RISC-V CPU will take that machine code, then execute those machine code. Okay, later on. Okay, probably after midterm exam, you are going to do class project. The class project is about the CPU design, digital logic design. Okay. Okay, this one, Minyoung.
Yes. Uh, Hardware, software stack in computer. First, application software is written in high-level language. Second, system software, compilers translates the code written in high-level language to machine code, and operating systems handling input and output, managing memory and storage, scheduling tasks, and sharing resources. And BIOS is basic input-output system. And third, ISA is interface between hardware and low-level software. Fourth, hardware, processor, memory, and I/O controllers.
Okay, thanks. Still abstraction slide, but more verbal explanation about each layer. Okay, from hardware to application software. Right? Hardware, you have CPU, memory, I/O devices. Right? Computer system, right? You have three components: CPU, memory, I/O devices. Because hardware is so complicated, it is providing abstraction layer called instruction or instruction set architecture. Okay. So if you understand instructions, you can fully control, you can fully manipulate this hardware, all different hardware. Okay. But instructions or machine code are still complicated, right? That is why someone is providing next layer. In PC case, we have BIOS, this very low level software, basic input output system. Okay, so this BIOS, what this BIOS is doing is when you turn on your computer, it is scanning your computer, figure out what kind of component you have, right? How big memory you have, from which company, Samsung, SK Hynix, and what kind of I/O devices you have. This guy, this is software, it's scanning your PC to figure out, do you have a keyboard? Okay, do you have mouse? And do you have how big storage? Okay, it is scanning. And and hand over to operating system. So essentially, operating system is managing hardware system, main memory, SSD, storage, right, and I/O devices, Wi-Fi device, Bluetooth device, keyboard, mouse, everything, right, and provide very convenient, super convenient environment to user, right? User, okay. So user can just use computer, okay, to surf the web, or you can develop your software, application software. Okay. So when it comes to this BIOS, there are two companies designing this BIOS, AMI and Phoenix Technology. Probably click on this. It will take you to BIOS. Have you seen this logo? This Phoenix Technology. When you turn on your computer, or AMI. Okay, let me click on this. Oops, no. What happened? Okay, let me click on this. Okay, AMI, this logo. AMI or this Phoenix Technology, this logo. When you turn on your computer, when computer boots first, then that logo appears, very, the 1 second, for 1 second, and disappears. That is the logo from BIOS company. Okay. When I work for Intel, I had a chance to look at BIOS from Phoenix Technology. It is very complicated, actually, software, right? Because it is managing this BIOS. This BIOS is managing this hardware. Okay, so to write this BIOS code, you have to have a very good knowledge, very good background on this hardware. How I/O devices are working, how keyboard, how mouse, and SSD, right? Those are interacting. Those are interacting with CPU. So you have to know those mechanisms to write this code. And BIOS is written. BIOS is written with these instructions. Instructions. Okay. We say if you write code with the instructions, if you write some software with instructions, 명령어, something like addition, So one example is like this: x5, x2, x 2. So this one example. If you write software using the instructions, we say you are doing assembly programming. Assembly, not C programming. Assembly programming, right? Very low level language. Low level language, right? High level language, C, Java, Python, those high level language versus this low level language. If you use, instructions to write program, you are doing assembly programming. Okay, so BIOS is written with assembly and C mix using these two languages, assembly and C these days. Okay, assembly and C. So to write firmware, this firmware, right? BIOS is also, you call BIOS as firmware. To write firmware, you should understand these instructions. Okay, firmware to write, not application software, firmware, right? Firmware. This one is firmware also, one kind of firmware. Okay. Okay, some high level, still high level view. So abstraction. Again, very important to see the forest, right? So that you don't lose, you don't get lost, right? Where you are in this big computer science forest. Okay, we are at the bottom, okay, layer. Okay, this one, Changsu.
Instruction. If you want to talk to foreigner, you should be able to speak their language. Likewise, to talk to a computer, you must speak its language. The words of a computer's language are called instruction. The collection of instructions is called instruction set. Different CPUs have different instruction set. x86, ARM, and RISC-V and have their own instruction set, but they have many aspects in common.
Okay, thanks. So if you want to talk to the first bullet, if you want to talk to foreigners, you should, if you want to talk to foreigners directly, I have to add that the word, right? If you want to talk to foreigners directly in person, you should be able to speak their language, right? So we have, in our class, we have some exchange students, right? Jasmine, you are from Spain?
I'm from
Jasmine?
Finland. Sorry, can you hear me?
You are from Finland?
Finland, yeah.
Okay, okay. So what kind of language do you use in Finland?
I speak Finnish.
Finnish?
Mhm.
Okay. So if you want to talk to Jasmine, you should study, Finland, right? And we have guy from United States, Angel. Are you there? Okay. Angel is from Texas A&M. If you want to talk to him, you should speak, English, right? You should be able to speak English, right? But what if you don't speak the Finland, right? And
Finnish.
English, yes. What do you have to do? If you are not able to speak English or Finland, then what do you have to do? You have to go through translator, right? You have to employ translator to talk to Jasmine and Angel, right? What is the translator in computer? Translator is a compiler in computer, right? So if you want to talk to computer directly, then you should speak computer's language. Computer's language are called instructions. Word of computers, I would say native language, right? Native language are called instructions. So example, right? Addition, that is native instructions. Okay. And collection of instructions or collection of machine code is called the instruction set. Okay, instruction set. And the bad news is, different CPU are providing different instruction set. So for example, x86, Intel, AMD, they are providing their own instruction set, own instructions. And ARM, smartphone CPU, also provides its own instruction set. Okay, RISC-V has its own. So the bad news is to understand its native, this CPU's native language, you have to go through, their documentation. But good news is there are many aspects they have. x86, ARM, RISC-V, they have many aspects in common. Okay, instructions are very similar. Okay, the shape is different, but the function is very, very, very similar. So if you understand one CPU, for example, RISC-V, thoroughly, completely, it is very super easy to understand other CPUs. So that is important. Understand one CPU completely. Okay. Okay. This slide for those of you who are eager to see instructions, right? Those are examples. Look at this. x86, Intel, and RISC-V. Right? Example is, look at this. It is, sometimes very intuitive. Here, instruction here, instruction, AND operation, right? AND operation, AND. Okay, and ADC means addition and accumulation. Addition and accumulation. So addition operation essentially. Okay, so and look at this RISC-V instructions. So that is also intuitive, right? Sometimes that looks very dangerous, right? Scary, right? But look at this addition, right? Add what? X5, X6, X7. So you are asking to add these two numbers and store the result in X5 register, X5. So function is very, simple. Function is very simple. Okay. Subtraction, right? Subtraction, right? Subtraction. Also X6, look at this comment meaning. 6 minus X7, right? And so on. So here, AND operation. AND operation, right? In digital logic design course, you have studied this AND gate, right? This AND gate, AND operation. So that AND operation is taking 32-bit and generate 32-bit output. So essentially AND gate. If I draw this one in detail, you have actually 32 AND gate inside the CPU, 32 of them. Because I don't want to draw this, 32, AND gate. So in short, okay, I draw like this. So each one 32-bit. Okay, this one 1 bit, 1 bit, 1 bit, 1 bit, right? So I don't want to draw, this, it is taking space, right? Drawing 32 different AND gate. Instead, just one AND gate and mark it. Okay, 32-bit input, 32-bit input, 32-bit output. Okay. So, function is very simple. AND operation, OR operation, those are logical operations, right? Logical. And this one, arithmetic, look at this, arithmetic, right? Arithmetic, addition, subtraction, arithmetic operation, and logical operation. So those are examples. So we will talk in detail about, really detail about, those instructions as we move forward. Okay. Don't worry too much. So it looks scary, right? And dangerous also, right? But it is not actually. It's very simple operation, super simple. Okay, if you want to see, if you want to know, if you want to check out instructions in advance, then those are the web page you can go to. Okay, they are providing document. So, and also our textbook is explaining in detail about the instruction. Also, you can check out this documentation, official RISC-V documentation, the specification, PDF. Okay, then they are listing somewhere. Okay, so instruction set. Okay. Somewhere, if you scroll it down, somewhere they are providing a table. The table, I don't know, where is that table? Okay. Okay, that is the one actually. Okay, that is the one. These, RV32I, those are instructions we are going to study in this class. Okay, so instruction and machine code. Okay, machine code format. For now, don't worry too much. Don't worry too much about that. Okay, we will get to the detail. Okay. Okay. So this one, Lesang.
High-level language, level of abstraction closer to problem domain, provides productivity and portability. assembly language, texture and symbolic representation of instructions, machine code, object code or binary bits of instruction and data.
Okay, thanks. Levels of program. High-level language is a C example, the code in C language, and compiler is translating. Compiler is taking this high-level code and translate that into instructions. Okay, instructions. And if you go through assembler, another program, that assembler is translating this multiplication instruction into these zeros and ones and zeros. Next, addition instruction is corresponding to this second line. For now, don't worry too much about this. I want to show you those are instructions and those are machine code, right? And one-to-one relationship. The first instruction, first line, okay, machine code. Second instruction addition, second line, okay. So one-to-one relationship. In general, we want to use a high-level language because it is providing productivity, right? You have your goal. You have you want to design some, you want to write some application program. If you use C or Java, Python, it takes little time to develop. Also, high-level language is providing portability. Portability means I think it's right. Portability means you can take this code and take it to Mac, or you can take it to your x86. So copy that code into x86, then compiler on your computer. Translate this code into Intel CPU understandable format, right? Again, that compiler in your notebook computer. Take this one, high-level code, into Intel CPU understandable code, machine code. And how about this MacBook? In the past, before 2006, 15 years ago, right? Before 2006, Apple used CPU called PowerPC. PowerPC inside Mac. And after 2006, Apple decided to use Intel chip x86. But these days, from I think 2020, last year, right? Apple started to use their own CPU, M1, right? One of you use M1 based notebook, M1 based Mac, right? M1 is what? M1 inside M1 there is a ARM CPU, smartphone CPU inside M1 CPU. Okay. So assume that you have PowerPC, very old MacBook. So the CPU is PowerPC. Okay, different, right? x86 and PowerPC. But you are still able to take this code and run it on MacBook because compiler here can translate this code into PowerPC CPU understandable code. Right? So that's why we call that portable. You take this code, you store that into USB stick, and put it into this computer, put it into that computer, right? Then compile it, right? Portable. You carry your code, then compile it on your machine, right? Then you are able to execute the code, portable. But so this code is portable, but once you compile this code into instructions, it is no longer portable. It is not portable, right? This code can be understood by, in this case, this CPU, MIPS. Only that CPU understand that code. Okay, that CPU understand this machine code. Okay, so the point is, if you compile that code, the instructions, machine code that is understood, can be understood by only that specific CPU. It is not portable. Okay, once you compile the code, right? So another, another graphical explanation, right? High level code. Okay. So if you use RISC-V compiler, RISC-V CPU compiler, that is C compiler translate that code into RISC-V instructions. Right? Those instructions can be understood by only RISC-V CPU. And assembler will take this code and generate to machine code. Okay, generate machine code. Okay, this one. Let me show you, one example with a demo. Okay, 재원. 재원. 유재원. Okay, probably microphone is not working. 혜림, 양혜림.
As high-level code to executable binary, what steps did you take to run your program Hello C on your Linux machine?
Okay, so that is the very first program you write, right, in language course. Okay, Hello World program. That is the very first program, right? And what steps did you take to run that program on Linux? Okay, so probably you use GCC, right? GCC, take this one as an input, hello world, hello. Then -O means option. I want output file to be hello, right? Hello is output file. Okay, then to run that code, you use the command hello. Then it will show you. Let me show you a demo. So I connected to my local machine. Okay, local Linux, box. Okay, and here. Oh, what is? Okay. So here I have hello world program. Okay, let me open hello.c. Hello world, a little bit different hello world. Okay, and it doesn't matter, right? Program, some program. Okay. To compile GCC -G. G means please add all the debugging option. In case something goes wrong, program does not work. Can you please turn off your microphone? Someone is Raesang. Okay, yeah. -G option is debugging option. In case, right? If the program is complicated, you write the code, then run the code, then something goes wrong, then what do you have to do? Right? You have to debug the code, right? Debugging the code, there would be two ways. You can add a lot of printf statement inside your code, or you can use GDB in Linux, right? GDB is debugger, right? GDB. So it is adding, many debugging debugging code, okay, inside your, program, okay. So let me use -G option here. Hello. I want output file to be hello, okay. What problem? What is the problem? Okay, there is, so how come I saw that? Okay. Okay, so working, right? So if you run this code, hello, then you see some message, right? Memory location is something. Okay. And then the file, this is the file generated by compiler, right? Hello, executable. We call that executable. 실행 file, right? Executable. 실행 file in Korean. Hello, right? The green file, right? We call that again executable in Korean 실행 file, or you can say that is binary, because this executable is composed. If you open this executable, then that is composed of ones and zeros, a lot of ones and zeros, only ones and zeros, because so that we call binary, right? Binary file. So can you open that hello? Try to open it, then it will show you what? It will show you a lot of junk, because it's composed of ones and zeros, right? And text editor VI is trying to show you what? Text editor trying to show you ASCII code, right? ASCII code. Assume that that is composed of I'm cooking up 1000 1100 10100001 something like this. Okay, assume that this executable 실행 file is composed of this. Then text editor VI, right? VI is trying to show you ASCII code corresponding to, okay, the first 8-bit is corresponding to what? And next 8-bit is corresponding to which character, right? So ASCII code. Google search with ASCII code, ASCII table. It is trying to show you a text character, right? That is why it is showing a lot of junk, right? Here, ASCII table. So that is okay. So ASCII table. So to display, to see, for example, uppercase A, then uppercase A, hex number 41, right? If you have 41, that is corresponding to character A, right? 41 is what in binary? 4 0 1 0 0 in binary. 1 4 0 0 0 1 hexadecimal number, right? Hexadecimal number. So if you happens to have 0 1 0 0 0 0 0 1 in executable, the text editor VI will show you A. Right? That is the how text editor showing the characters. But again, this binary, it shows only junk, right? Then can I see some information about this binary? Yes, you can see with what this this command object dump. Okay, object dump is doing this. Let me show you. So I used GCC, right? GCC to translate hello.c to hello, right? Hello, that is executable. So that is composed of ones and zeros, right? It is a text-based code, and GCC compiler. Our compiler translated that into executable binary. But to human, it does not provide any useful information. Open this one, then all junks, right? So can you see some useful information from here? From this executable? Yes, you can. With object dump. So that is, if you run this code, object dump, then this one is taking this executable as an input and translate that into human understandable code. Okay, object dump back to some human understandable code. Double code. Okay. So let me run that code. -s -sd. Okay. Command. Object dump. Okay, minus S, some option SD. Take hello as an input. Then I want my output to be hello.dump. Okay, so that I have hello.dump generated now. Let me open hello.dump. So look at this. So and search with main. Look at this. Familiar, right? Familiar function. So we in C code we use the main, int main, and open curly bracket. And I declare this local variable int I, assign 10 to I. Let me open hello.c. That is the original code, right? Int I is equal to 10, right? That is here, 10, 10, and printf statement. Okay. So compiler translated this opening curly bracket with 1, 2, 3, 4, 5, 6 push instruction, move instruction, solve, move, XOR instructions. Okay, this opening curly bracket, even opening curly bracket is translated into 1, 2, 3, 4, 5, 6. Those are instructions Intel is providing, x86. Okay, and this number 55. 55 is machine code. Machine code for this push %RBP. That instruction is corresponding to this machine code. And next instruction, move, RSP, RBP. That is corresponding to that machine code, 4889E5. Okay, and so on, right? Subtraction, machine code 48A3EC10. Okay, those are machine code. Those are instructions, right? And the next, this number, those are memory location. So your this machine code 55 is stored at this memory location. So if I draw memory, so main memory. So you have 5 stored somewhere, right? Where? According to that file 400596. At that location, this machine code is located. Okay, that is the one. So memory location, we call that address, right? Address, or memory location, memory address or location. And this data or instruction is located. Printf, right? Look at this printf statement. Okay, that got translated into 1, 2, 3, 4, 5, right? And printf, I haven't written printf function, right? It is provided by this header file, right? So if you look at this instruction, it is calling, right? Call instruction. We don't know we don't know in detail about instruction, right? But by looking at this word call, it sounds like it is calling something, right? Call, right? Calling what? Printf. Okay, we don't know for sure, but we have some feeling, right? By looking at the code, right? So don't worry again too much about this. This is Intel, right? We are going to study RISC-V, right? RISC-V instructions. The point of this slide is this. After you compile the code with GCC or Visual Studio Compiler, you can translate it back to a human readable form of the code using object dump. Okay, if you are curious about this executable, what kind of instructions, what kind of data are there, then you can use object dump to translate back to human readable form of the code, because it is not human readable form, right? It is composed of ones and zeros, right? So in this case, in this simple C program, look at this. Simple C program, okay. We define two macros, A, B. A is 3, B is 5. Super simple, code, main, right? It is printing out, A, B, then subtraction output. It is calling this function, subtraction, myself. Myself is defined here, right? Subroutine, function, or procedure, right? So you have two arguments. It is taking two arguments, A and B, right? A and B, A is 3, B is 5. So taking 2, then do subtraction, okay? So result supposed to be -2, 3 minus 5, right? So this printf statement is printing out, right? 3 minus 5 is equal to -2. So if you compile the code, and compiler will give you this instruction and machine code, right? Opening curly bracket, corresponding to this subtraction operation is corresponding to 1, 2, 3, 4, 5, 6 instructions. By looking at this, look at this. You are asking this myself, right? Myself. You are asking computer to do subtraction. And scanning this code, you hit solve some very suspicious. Okay, I think it is. We haven't studied instruction yet, but by looking at the word, we feel like okay, it is doing subtraction, right? Solve. It goes solve, right? Subtraction. By looking at this code, okay, solve. ECX, EAX, subtraction operation. Okay. Any questions so far? Okay, let's move on. Okay, so it is machine readable form of the code. We call that machine code. Again, green one, machine code, orange colored code, instructions, and black are memory location, like address. Okay, address. Okay. So what kind of steps you have to take to compile the code? This slide is showing you some detailed steps to compile the code. Okay, so we use only GCC, right? On Linux, we use GCC to translate this code into the executable. But if you want to, the detailed compilation steps are composed of four big steps. Okay, 4 big steps. The first one is pre-processing, and second, actual compilation. Third, assembler. Then final step is linker. So preprocessor is doing, okay, preprocessor is expanding C program. So in the previous example, expanding means, okay, you are including this header file. Also, you define those macros, right? So preprocessor is going to find out this header file and replace that with actual contents of the header file. I'll show you a demo, okay? And the macros, A, B, you declare those two macros. If you do pre-processing, then you are going to replace these A and B here. A, B, those will be replaced with actual, the number 3 and 5. That is pre-processing. And compilation is the compilation. Take expanded C program and generate assembly code. Assembly code is composed of instructions, those instructions, addition, subtraction, those instructions. Then assembler, this assembler will take instructions and generate binary, ones and zeros. We call that object code. Okay, and then you have to include a library, because some functions like printf, we use printf a lot, right? Printf. In C language, you use open, file open, right? File close, file exit. Those functions, someone, right? Someone is providing these functions for you, right? You haven't written that code, right? So those functions are provided by library, right? Library. So in the final step, you take the linker, right? As the name implies, it is a linking your code and the code in library, and generate final executable, right? And the loader, after generating final executable, you execute with that command, right? In Linux, hello, then enter, right? Then loader, right? Then loader, this loader will load, take this one and store into memory your binary, hello, right? It's executable. Then CPU, now loader will load this code into the main memory, your code, right? And CPU will read machine code and execute it, right? So this yellow, right? Yellow box is still human readable form of the code. C code, expanded C code, and assembly code are human readable form of the code. But after going through assembler, these green boxes are not human readable form of the code. But if you really want to see, if you want to really interpret the code, you can do that actually. But I don't want to do that, because ones and zeros, I don't want to look at ones and zeros, right? But there is a way. There is a way to to analyze this green code. Okay, so let's go through each step. Okay, each steps. Okay, this one, 한지성.
High-level code to executable. The command GCC hides all the details. Compile simple sub.c with GCC with simple under sub.c or simple sub. You will see all the details of what GCC does for compilation. Compilation goes through several steps to generate the machine code: pre-processing, compilation, assembler, linker.
Okay, thanks. Actually, if you compile with GCC is hiding all the low-level detail, right? GCC compile, take this C code, compile this C code, and generate executable, right? It is very silent. It doesn't show you anything, right? But if you add this -v option, it will show you everything. Okay, it will show you everything GCC is doing. What GCC is doing. -v is verbose option. V, verbose. Or talkative option. Show me everything option. Show me everything what you are doing, right? So let me show you. So I have, let me compile it here. So we have simple solve, this code, simple sub, right? Same code. The thing I showed you, right? We have two macros defined, A and B, and simple subtraction, right? Myself. This function, myself, takes two argument, OP1, OP2, do subtraction, then return the output, right? So printf statement will print out A and B and output. Very simple, right? So GCC, let me open that here. Because let me open it here. Better to open it here. Okay, let me compile it. GCC my simple self. Then -o. I want output file to be this one. A warning, right? It's okay. A warning. So I have simple sub generated. So you can execute simple sub. Okay. 3 minus 5 is equal to -2. Okay. So I use GCC and it is very silent. It doesn't show you anything. But if you add -b option, talkative option, show me everything option, right? Showing you this bunch of command it is going through. Okay? So let me clear. Okay, do it again. Get this. So from here, it is executing this long, complicated command to generate final binary. Okay, so this talkative option -b. Okay, so what it is doing with this long command is, is this. It is doing pre-processing, actual compilation, assembling, and linking. That's why it is pretty long, right? Let's go through one by one. Okay, first pre-processing. 정훈, can you? 노정훈?
Yes. Pre-processing used to expand macros and header files included CPP simple sub.c to simple sub.i.
Okay.
Open.
Okay, that's enough. Thanks. Stop there. Okay, pre-processing first. Okay, so take the same code. Let me execute CPP. Where is CPP? Which CPP in Linux? Then that CPP is located at USR bin CPP here. Okay, so if you want to know about CPP, then info. You can use this command info CPP. It says C preprocessor. Okay, C preprocessor. Okay, just exit. Let me show you now. CPP, what was the command? I have a short memory, okay? Take this one. Simple. Then I want output file to be .i. Okay. Now you have .i generated. .i, right? So open that .i. Then the original code, right? Original code is very simple, right? Here, include stdio header file. Where is main? Here, look at this. Look at the line number. Line number 854 main. Okay, so from line number 1 to here, line number 1 to line number, that is header file, stdio.h. So actual content of the header file got replaced. Okay, got replaced. And look at this. Look at the code main, right? 3, 5. So A, B, those macro got changed with the actual number 3 and 5, and 3 and 5, right? So pre-processing is expanding header file, and the macro got replaced with actual number. Okay, that is pre-processing. And actual compilation. 정훈, can you please? The first split, please. Only.
Actual compilation of the pre-processed code to assembly language for a specific processor.
Okay, thanks. So the command is this. You use GCC, okay, then -s option and take this one as an input. the one you just generated, this output, you take that as an input. Right? Let me do this. So exit, then GCC minus S simple sub.I. Okay. The warning, that's okay. We can ignore. You have what now? Dot S. Dot S generated. Okay. So open that. Simple dot S. Okay. Here, look at this. Search with main. It is showing x86 is Intel instructions. Okay, so main function, right? This main function was translated with those instructions: push, move, call, right? Because we don't know for sure. We don't know for sure about the function of those instructions, but by looking at this word, right? Call. Here, actually main, you are calling myself, right? You are calling this subroutine, right? Main function, caller. This is caller and this is callee. You are calling this myself. So that is why, main, inside the main, you are calling, you are using this one, right? Call myself. We don't know for sure about those instructions, but by looking at this, we got some feeling, right? Okay, you are calling something, right? Call, function, right? And then myself, where is myself? Here. Scroll it down, the myself, right? Myself is doing what? Myself is doing, I don't know for sure about those instructions because we haven't studied x86, but look at this. So SUB. It sounds like doing subtraction. Sounds like doing subtraction, even though we don't know for sure, right? Because you are here. You are asking computer to do subtraction operation. Okay. So that is actual compilation. So compilation take expanded C code. Okay, go back here. Expand compilation take expanded C code, generate assembly code. Assembly code is composed of instructions. Okay, instructions. Those instructions. Assembly code is composed of those instructions. Okay, then next step. Jongwon, can you? First line only.
Convert assembly language into machine code and generate an object file.
Okay, now you want to take this assembly code and you want to generate machine code. Machine code, again, composed of ones and zeros, right? You can use AS. AS is assembler, okay? Let me do this. AS, take simple solve as an input. I want output to be simple solve.o, okay? Object code. Then .o, right? .o generated. But if you try to open it, you cannot see. With the text editor, you cannot see. It will show you, junk information, all junk information, right? Because binary, right? Do I have hex edit? Oh, do I have hex edit? Okay, then you can use hex edit to open probably this. Look at this. Now you can see the contents, right? Your binary code as in hexadecimal number 7F454C. Those are contents actually. But using text editor, you cannot see because text editor will show you ASCII code corresponding to each 8-bit. First 8-bit, 7F. Okay, that is corresponding to which character? Okay, 4-5, that is corresponding to what? Which character? According to ASCII table, right? Okay, close it. How to close it? I don't know how to close. Please. Anyone know how to close it? Q. Press any key. F1. Anyone know how to close it? How to exit it? Oh shoot. Oh man, I cannot exit. Unknown command. F1 for help. F1. How to close it? Oh, man, very tenacious. Control C. Control C. Control C. Thanks God. Thanks God. Okay. Okay. Then final step. Linker. Okay. That is okay. Enum. Control C. Yes. Yongsub, thanks. Yongsub. Enum, please. Okay. We are running out of time. Let me do that. Okay. Linker is the final step, right? So linker is, let's go back. Linker is taking the code I generated, and also you should include the libraries. Okay, you are going to you use in your code, right? So your code and library code, linking these two together. So the command is very complicated. So you can use LD. LD is a linker command, and you want to take the output generated from assembler, right, .o, and I want output to be this one, executable. But in between these two, LD and this one, you know, very long options. Very long options you have to. Basically, you are specifying the location where library is placed. Okay, where the library is, right? You are specifying the library path, right? So very long command. It depends on Linux version. This path is different depending on Linux version and OS. So complicated, right? So I prepared. Last night I figured out the command. I figured out the command from this GCC, right? GCC, not the GCC. From this command, this long command, I was able to isolate this linker, okay, linker command, and found that this is the one you have to use, LD, blah, blah, blah. Then take this one as an input, output is this, okay? So let me execute that. I don't want to, type everything here, right? So let me copy. Linker, let me, linker command, link command, okay? Then remove everything except this linker, okay? Then and case command, right? Make it read executable plus X, okay? Change mode, right? So now it is executable, right? So link lnk command. Okay, now we have what? We have this binary generated. 1144 just generated, right? 1143. Right? Let me remove in case someone is suspicious, right? So remove this. Okay. So regenerate the code with linker command. We have this code generated 1144. Okay. So now execute it. Simple. So same, right? 3 minus 5 is equal to minus 2. So after generating final executable, you can run it, right? You can run it with this command, then output. Okay. 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 Let me talk a little bit about the assignment, right? We are running out of time. Okay. We are, time's up, so I don't think we have time to explain the final slide. Final slide is about cross compiler. Let me quickly explain what the assignment is. We are in this class. We are going to study RISC-V CPU, right? We are going to learn RISC-V CPU. So from this high-level code, we want to somehow generate RISC-V instructions, RISC-V machine code. But the problem is, most of the people use Intel machine, Intel x86, right? So that means if you compile this code, then your compiler will generate Intel instructions, not RISC-V instructions. There is a problem, okay? So we don't want to study Intel machine code, Intel instructions. We want to study RISC-V machine code. Then the question is, how to generate RISC-V instructions from this C code, okay? You can use cross compiler. Cross compiler will do the job. Cross compiler take this one and generate RISC-V code. So the first assignment is about First assignment is about installing cross compiler. Okay. So I'll talk a little bit in detail about cross compiler. So first assignment, second bullet, cross compilation, cross compiler. To do cross compilation, you have to install the tool, which is the instruction is here, RISC-V cross compiler with Eclipse. So essentially, I'm asking you to install several tools, starting from JRE, Java runtime environment, and Cygwin, Linux-like environment, and cross compiler. The cross compiler I'm providing. Then Eclipse. We want to use a GUI environment, not command-based. So those 4 steps, right? JRE, Java runtime environment, Cygwin, and then cross compiler Eclipse. Okay, that is the environment we are going to use to cross compile high-level code to generate RISC-V instructions. Okay, sorry, time is up. That is it for today. Any question? Where can I find PPT you used in class? On class page. Class page here. I posted everything right here. So this is the first one. Sorry, this is the one I used today, machine code. Any other questions? Yes, I think today's lecture would be 90%, more than 90% enough to do the homework. So on Monday, I'll talk some more about cross compilation. Okay, but for now you can just follow the instructions. Okay, this one, cross compile with Eclipse. First, install the tool. Set up the environment. Okay. Then on Monday, I'll talk a little bit more. Okay, any other questions? Okay, that's it, guys. I'll see you next time. Bye. Okay, thanks.
Professor,
Mhm.
Can I ask you a question?
Yes, for sure.
Yes.